Bismillahirrahmanirrahim. Assalamu alaikum viewers. Welcome to my channel. And in today's video, we'll try to understand the geometrical interpretation of our derivatives of a function in context of the slope of a tangent line, as it is mentioned already with the heading you can see. So for this purpose, I would like to draw a figure representing a curve of any function, and with the help of that we'll try to understand the concept or the geometrical interpretation of the derivatives. So let's have a look to the figure. Okay, so I've just tried to maintain a Cartesian plane, and I'm just focusing on the first quadrant just for my convenience. And I'm going to draw a graph of any function f of x. You can see here that I'm just using a single variable function, and over here at the y-axis I'm going to plot the values of my f of x, because f of x, the function is based on the independent variable x. Okay, so on the y-axis we are using the values of our f of x, and on the x-axis we are simply going to use the value of x, and we just plot a curve and representing this function equation. And for example, on plotting, I just got a curve like this, just for instance. Okay, and this is a curve representing y equals to f of x, and f of x is any function. All right, now just assume that you are having a certain point here, for example at this position, and I just name this point as my point P. Okay, having the abscissa or x coordinate right over here, I just call it x1, and the corresponding value of your y, which is your f of x1, is right over here. Okay, so you know that this is a two-dimensional setup. This is a plane, obviously, so every point lying on a plane is expressed in the ordered pair of two tuples. So it is going to be written like this. This is the x coordinate and this is the y coordinate of this point P, right? This is it. Now in the same way, I just maintain another point here and I just call it Q. I just call it Q, and its x coordinate is so projected at this position, and it is your x2. In the same way, the corresponding y value is mapped over here. It is f of x2. Okay, so this Q is expressed with the coordinates x2 and f of x2. This is your x coordinate, this is the y coordinate that you also call it as abscissa and ordinate. All right, so this is it. Now these are the 2 points lying on this curve, which is the graph of this function f of x, no matter what the function is. All right, so if I just try to join these 2 points on the curve, it is going to be joined by means of a straight line, and that straight line which is joining 2 points on the curve is called the secant line. All right, let me draw it in a rough over here. Later on I'm going to join these points. Just try to understand that, for example, this is a curve and these are the 2 points, and if I'm trying to join these 2 points by means of a straight line, like this, and this line is called a secant line. All right, because it is joining 2 points on the curve. And a line which is touching just 1 point on any curve, that line is called the tangent line. You call like this. If this is a tangent line and it is touching just 1 point on the curve, this is what you call a tangent line, and the corresponding point through which it is touching is called the point of tangency. This is called the point of your tangency. All right, so this is it. So over here you can see, once when I'm going to join my point P and Q, I'm going to have a secant line and it looks something like this. Let me join it. Okay, like this. This is the secant line that I have just obtained here. Now let's move ahead and see that once when I try to calculate, I try to measure the value, the length from the origin to this point x1. I just call this length equal to my x1, and the length from origin to this point x2 is represented by this value x2. This is an obvious thing. So it means that once when I subtract this value from this value, I'm going to get this length from this point to this point, and this is something that you call del x. Okay, the distance from this point to this point is the difference of x2 minus x1, and is represented by del x, and also you can represent it by another representation, this one. It is your choice which option you're selecting for the representation. Okay, so this thing tells that actually your del x is x2 minus x1. In the same manner, as this is your y-axis representing the function values, so the value from origin to f of x1, you can call it y1, or simply you can write as f of x1 as well. And the distance from the origin to your f of x2 is from here to here, is represented by y2 value. Also you can call it f of x2. So the distance from this point and this point, the distance between these 2 points, if the difference of your y2 and y1, once when you subtract y1 from this y2, you're going to get this portion value left. So you can call this length as your del y, or also we are going to represent with another form. Let me write it over here. So this is your del y, and it is the difference of y2 minus y1, or I can also write like this, that my del y is the difference of my f of x2 minus f of x1, and also I can interpret my f of x, my x2 at the place of my x2, I can write x1 plus del x. If I just move this x1 over here, then only x2 is going to be represented as x1 plus del x. So I can write my del y as this, x1 plus del x minus f of x1. Alright, so this is the difference. This del y can be interpreted like this, and this is your del x, and it is simply written in this form. I hope it's clear up till now. So this is the slope. The slope of this secant line can therefore be expressed like this. Slope of the secant line segment PQ can be expressed as your rise over run. Okay, this is your rise and this is your run. So actually you are, let me use a different color. Let me use a red color. So you are running from this point to this point, and then you are rising from this point to this point. So this thing is representing the ratio of these two activities, is representing your slope value. Okay, so this is your, what you say, del y upon del x. So how about if I just write my values here, that del x, del y is your, can be written like this, upon your del x. All right, this is it. So this is the slope of your secant line of these 2 points P and Q. I hope it's clear up till now. Now, how about if I just say that keep your point P fixed and just start moving your point Q towards your point P like this. And also you can keep your Q fixed and you can start moving your P towards Q, that's your choice. So once you see when one point is fixed and the other one is moving towards it, then you can see that this distance is going to reduce because your Q will keep on moving towards here. So this thing is going to reduce the value of your del x. So once if it keeps on moving towards P closer and closer, so this thing is going to minimize your del x as closer, very close to 0, and make sure that your P is not overlapping your Q. I mean, P is not equals to Q, neither Q is going to overpass your P. This thing is not happening. Only Q is getting closer and closer to P, and it will remain behind P. It's like that, okay? So once when if your P approaches to Q or your Q approaches to P, that's your choice, then what is going to happen? This del X is going to reduce, because definitely Q is reducing, Q is moving towards it. So this thing is going to minimize the value of your del X. Okay, for example, if Q approached from this point to this point, then this thing, now this time the Q is over here. So X2 is over here. So del X has now been reduced. So if Q gets more close, or like if Q comes over here, then now Q position is over here, and now X2 is over here, and now del X is very small now as compared to what it was in the beginning. So once when your Q is getting closer and closer to P, or P is getting closer and closer to Q, whatever, so this thing is going to minimize your del X such that it becomes closer and closer to 0. Make sure it is not becoming equals to 0, because Q is still behind your P. It is not getting equal to P. It's not overlapping on the P. So once when this thing happens, then now what is going to happen to the figure? Let me redraw it over here. Like if I just redraw the figure once again, and you are having a curve, and this is your point P, and your Q was here, and it gets approaches to P as much as closer and closer as it could be. So now your Q and P get so close that they look like one point, a single point, though they are not, but it looks like that they are one point. So now this time you are going to draw a tangent line passing over this point like this. Okay, so if you just apply a limit over here, if you simply apply a limit over here, such that our del X is approaching to 0, means once when my del X, when my Q approaches to P, your del X approaches to 0. So this thing, Q gets so much closer to your P that they looks like a single point. Both these points looks like appears to be like a single point, and you are going to draw a tangent line passing through or touching through this point, and then you are going to have a slope of that tangent line. So in other words, you can say that the limit of this secant line is representing the slope of a tangent line, which is this one. Then your Q approaches to P, when you're this, then in this way you're going to have a tangent line over here, and the slope value of this tangent line is actually the limit of the slope of this secant line. And make sure that the limit value should be well defined, and if the limit value is well defined, then you are going to say that this the limit of this secant line, which is actually the slope value of the tangent line, is expressing the derivative of this function f of x at particular point P, okay, representing the abscissa x1. All right, so I can write like this, that the limit of my del is quite horrible, and I hope you can understand that the limit of the slope of my secant line, which is actually representing the slope of the tangent line, the limit value of the slope of the secant line is equal to the slope of the tangent line. Okay, it is equal to the slope of tangent line at this point, all right? And you can also call it the slope of the tangent line of the graph. Okay, no matter what point you are, what point of the graph you're looking at, and you're having a tangent at that point, then simply you can call it the tangent of a graph at the particular point. So you are having, we are observing the tangent line at this point, so we can call it that this is the slope of this tangent line of this graph of the function f of x. Okay, so this slope of the tangent line is representing the derivative of the function f evaluated at this point x1. Okay, so we can also interpret it in this way, that the derivative is the instantaneous rate of change of the function behavior with respect to its independent variable, because there are several values on the basis of which the x is defined, and sometimes it is defined on the basis of your t, sometimes it is defined on the basis of your x, and so on. So whatever the independent variable is, the instantaneous rate of change of the behavior of your function with respect to the independent variable is actually the derivative of that function evaluated at that point. So you see, we are going to write this limit of the slope of the secant line, which is actually the slope of the tangent line. We can also represent it by this notation. Okay, and make sure that once when G.W. Leibniz and Sir Isaac Newton both belong to, they were contemporaries of that time in the 17th and 18th century. So they were independently working on the same concept of the derivatives. So they just come over on this concept that the ratio of this small change in dy with respect to the small change in dx explains the derivative of a function at a certain point. But at that time, both were unaware that actually it is the derivative is the limit of the slope of the secant line, which is equivalent to the slope of the tangent line, and it should be well defined. So at that time, both those great mathematicians were unaware of the concept of the limit, and they simply represent the derivative by means of the dy by dx, but actually the instantaneous concept is incomplete unless we just apply the representation of the limit, because actually the instantaneous rate of change explains the rate of change of a function between the interval that you are unable to calculate. For example, if I just say that at 5 p.m. The subject XY, Mr. XY, has just covered a distance of 5 meters, then how much distance he is going to cover it after 5 p.m. and 2 nanoseconds. So in the 2 nanoseconds, how much change in the distance that he is going to experience. So this thing is quite difficult to observe or to calculate. So at such kind of state of affair, you use the limit concept because it covers the instantaneous rate of changes, which are extremely negligible to observe. So that's actually the story behind. So I hope you have understood the concept of tangent line and the connection of the slope of the tangent line with that of the derivatives, and the functions which hold a derivative or which hold in the state instant, which are well defined in their instantaneous rate of change. For such functions said to be differentiable. Okay, so if at a certain point on a curve, if the rate of change is not well defined, then you say that at that point the function is not differentiable because its derivative does not exist. So that's what you say. So that's all for today. So if you find this video helpful, I humbly request you to subscribe to my channel, hit on the like, and share this video as much as you can. And that's all. And in the next video, inshallah, we'll try to cover Rolle's theorem. Take good care of yourself, and Allah Hafiz.